Every star in the universe is a voice. A voice that vibrates, that sings, that resonates through the void as if the entire cosmos were a gigantic resonating chamber. Yet for billions of years, no one had ever been able to hear this silent choir, until one day, someone found a way to make the stars speak. Asteroseismology is the science that listens to the heartbeat of the universe. Not the human heart, but the hearts of stars. Slow, deep, imperceptible pulsations that travel through stellar matter like waves in an ocean of incandescent plasma. Waves that we cannot hear with our ears, but that the most sophisticated instruments can detect as tiny variations in brightness or surface motion. It is a young field, but one capable of revolutionizing our understanding of stars. Because if spectroscopy and photometry reveal the surface, asteroseismology opens the doors to the interior, where the most mysterious processes occur: nuclear fusion, convection, gravitational collapse, deep rotation. It is like moving from observing the skin of a living being to listening to its beating heart, its lungs expanding, its blood flowing. It all begins with a simple and wonderful concept: stars vibrate. Just as a bell resonates after being struck, a star can oscillate when disturbed. These oscillations are not random, they depend on mass, composition, temperature, and internal structure. Studying the frequencies of these vibrations is, in essence, performing a celestial CT scan. Each type of wave penetrates to different depths and returns with specific information. Some reflect off the outer layers, others reach the core. The first insights date back to the 1960s, but it was with helioseismology, the study of the sun's oscillations, that this discipline took concrete form. With instruments such as the Global Oscillations Network Group, GONG, and the Solar and Heliospheric Observatory, SOHO, scientists began recording solar vibrations and mapping its internal structure. They discovered, for example, that the sun does not rotate as a solid body. The equator spins faster than the poles, and the core behaves in an even more enigmatic way. But the true breakthrough came when it became possible to extend observations to distant stars. Through space missions such as Kepler, TESS, and now Plato, we can study thousands of stars simultaneously, observing them for months or even years with extraordinary photometric precision. Every variation in brightness is analyzed as a musical note. From these notes, scientists extract primary and secondary harmonics, build vibrational profiles, and construct theoretical models to compare with data. And the results are astonishing. Thanks to asteroseismology, we can now measure the mass and age of distant stars with extraordinary accuracy. We have discovered that many red giants conceal an active core, and that sun-like stars follow evolutionary paths far more diverse than we once imagined. We have found stars that rotate asymmetrically within, or that contain stratified zones exhibiting entirely new physical behaviors. Perhaps the most powerful analogy is with music. Every star is an instrument unto itself. Some sound like a deep, somber cello, others like a high, trembling flute. And these melodies are not just poetic expressions, they contain data, codes, maps. One day, we might even identify stellar families not only by their position or chemical composition, but by the voice they emit, as if each star possessed a unique sonic fingerprint. And that is not all. Some pulsations, such as those of delta Scuti-type variables or subgiants, are so complex that they generate genuine chaotic symphonies. To understand them means constructing mathematical models capable of simulating an entire stellar lifetime, minute by minute. It is as if we had access to the secret diary of stars, written in waves. Today's challenge lies in combining asteroseismic data with information from other astrophysical disciplines, uniting light and sound, spectrum and vibration, chemistry and acoustics. It is work that requires immense computational power and sophisticated models, yet it promises extraordinary revelations. The ability to predict the death of a star, the formation of a black hole, or the birth of a supernova. because everything leaves an echo, and every echo can be deciphered. But what fascinates most is not just the technique, it is the cosmic poetry behind this approach. For the first time, we are not merely observing the stars. We are listening to them. And what they tell us is as vast as the silence that shrouded them for billions of years. There is something profoundly human in the idea of listening to the heartbeat of the stars. Perhaps because, deep down, our hearts also vibrate. We, too, are creatures of oscillations, traversed by waves, electrical, acoustic, emotional. Asteroseismology, then, becomes a bridge, a shared language between us and the heavens, made of frequencies and harmonics. And the more we learn it, the more we realize that the music of the stars tells stories that transcend science itself. Some of the most intriguing recent discoveries involve the so-called mixed modes, hybrid oscillations that travel both as pressure waves, P modes, and gravity waves, G modes. The former cross the star's outer layers, while the latter propagate through its darkest depths. When a star is in transition, say, when it exhausts the hydrogen in its core and begins fusing helium, these two types of waves can interact, merge, and interfere. The effect is like a musician playing two instruments at once, producing a melody entirely new and unpredictable. Thanks to mixed modes, we can now directly observe what happens in the cores of red giants. We can tell whether a star is still fusing hydrogen in a shell around its core or has already ignited its helium engine. It is like reading a stellar fuel label simply by listening to its vibrations. Once, such information belonged solely to theoretical models. Now, it is measurable, verifiable, accessible. At the same time, interest is growing in asteroseismology applied to stellar clusters. Studying the oscillations of stars born together, with the same initial composition and age, allows scientists to refine evolutionary models. It is like observing a classroom of cosmic twins, who matures faster, who ages more slowly, who strays from the expected trajectory. Every anomaly is a clue, a lead toward what theory has yet to explain. But the true horizon opens when we apply asteroseismology to stars that host planets. Their oscillations can reveal, with great precision, the star's mass and radius, thus improving estimates for the planets that orbit them. In other words, to determine whether an exoplanet is truly habitable, we must first understand its sun precisely. It is a crucial step, often underestimated. Every error in characterizing the star reflects directly on the planet's properties. If we dream of finding another Earth, we must first learn to read the song of its stars. And yet, much remains to be discovered. Some stars exhibit unstable, erratic oscillations, difficult to interpret. Others appear completely silent, devoid of detectable pulsations. There are still mysterious phenomena, such as non-periodic phase shifts or sudden frequency changes. Some scientists even hypothesize the existence of stellar quakes, sudden events capable of temporarily altering a star's internal structure. In a sense, we may be witnessing invisible cataclysms, detectable only as deviations in a star's usual song. In this context, artificial intelligence is becoming crucial. Machine learning algorithms are trained to recognize hidden patterns in light curves, to classify stars by their frequencies, to detect anomalies the human eye would never notice. It is an alliance between human intuition and computational power, between instinct and statistics, a partnership that opens dizzying perspectives. Yet perhaps the most evocative part is what we cannot yet prove, only imagine. What if there were civilizations out there that, like us, study the universe by listening to it? What if they had found a way to transmit information not through radio waves, but by modulating their star's oscillations? It is a distant hypothesis, yes, but one full of wonder. The possibility that the message of an alien intelligence lies hidden within the vibrations of an alien sun, awaiting interpretation. Ultimately, asteroseismology teaches us that the universe is not silent. It is a pulsating organism, vibrating on every scale, from subatomic particles to entire galaxies. Every structure, every system, every form of matter emits oscillations. Even the vacuum itself, according to certain quantum theories, is not truly empty but a sea of continuous fluctuations. Thus, listening to the stars becomes a universal act of listening, tuning into the very fabric of reality. The age of merely observing the sky through telescopes is over. Now we listen to it, translate it into music, decode it into mathematical harmonies. And every new frequency discovered is another word in the great cosmic vocabulary. Because perhaps, in the end, the universe was not created from nothing. Perhaps it was born from sound, from a primordial vibration that still resonates, hidden in the depths of the stars. And we, tiny beings on the surface of a common planet, have only just begun to tune our ears to understand it. If you've made it this far, it means you love curiosity as much as we do. If this journey has inspired you, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.